Welcome to the first colloquium of this academic year. So we will have a series of colloquia that are available on the webpage of Colloquium Patavina. This colloquium today is specially tailored for students, so I'm really glad to see lots of young faces. And if I may remind you, after the colloquium, there's a little refreshment on the ground floor of Torre Archimedes, so everyone is welcome, and can talk to the speaker and to all of us there. So it's my pleasure to have here today Professor Lidia Angelei Hugo, who is a full professor at the University of Verona since 2016. She did a PhD in Munich some time ago, in 1991. Had several positions in Barcelona and in Varese, and is now in Verona for some years. It's particularly heartfelt for me to introduce her here today because she is a representation theory with lots of impact in lots of young mathematicians, in particular on my own career. And today, in particular, she is the grant holder of a Fondo Italiano per la Scienza. So it's a big grant awarded a couple of years ago, and I believe, as far as my research could go, the only pure mathematician to have been awarded this grant. So it's my absolute pleasure to introduce her, and she will talk about the representation type of an algebra.
Thank you very much. So thank you for the invitation, and yeah, let me start right away. So I want to tell you something about representation theory of algebras. This is a research area that has started, say, around the 1970s and has grown very rapidly. And here in Padova there is a group working on this, and in Verona there is a group, and in many other places all over the world. And yeah, so let me start by saying what an algebra is, recall what an algebra is. What is an algebra? So we start with a field, and we take a vector space over this field, and we define a multiplication on this vector space. And of course we want, so it becomes then also a ring with this multiplication, and the two structures, the structure of a vector space and of a ring, are compatible. For example, so the ring of polynomials is a ring, but is also a vector space of K, and the two structures are compatible. So this is first example that should come to your mind. Then matrices, so 2 by 2 or n by n matrices form an algebra, and also lower triangular matrices or upper triangular matrices form an algebra. And then, for example, if you take a finite group, you can define an algebra by taking as a vector, by looking at the vector space that has as a basis the group elements, and defining the multiplication by using the operation of the group, and this is also an algebra. Now, in representation theory, we study algebras by looking at their representations. And when I say representations, in fact, I mean modules. What are modules? A module is, again, a vector space over the round field that has a multiplication with elements of the algebra, and again, the two structures have to be compatible. But rather than looking at a single representation, we are interested in the collection of all representations. So we want to look at the category of all modules. This is usually very big and very hard to investigate. So we look at the finitely generated modules, but this is still not always easy to study. And therefore, one employs certain reduction techniques. So we want to study this category, say, of the finitely generated modules over our algebra. And then we try to reduce the problem to simpler situations. And there are, for example, the first thing you could do, you could decompose the category. You decompose it in two smaller parts that are still big enough to reconstruct all objects of your category. And this leads us to the notion of a torsion pair. Then another possibility is localization. This is something that is done in commutative algebra. So the idea here is that you reduce your questions to certain rings which are easier, have an easier structure where you can work better. And then another possibility is to decompose the modules in your category. So what does it mean? You write them as direct sums of smaller modules, and you keep doing this until you get to some modules that you can't decompose further. These are like building blocks for the big module. And this can be done and is a very good approach because of the theorem of Krull-Remak-Schmidt. Because when you have a finite dimensional algebra over a field, then we know that every finite dimensional module, so every finitely generated module, is a direct sum of indecomposables. So it can be decomposed in this way to these small building blocks. And this decomposition is essentially unique. So that means that if we want to study the collection of all finite dimensional modules, it's in fact enough to look at the indecomposable ones, because these are the small pieces that you use to construct all the others. And so this is an important point, and then the next important point is the theorem of Gabriel that tells us that when we have a finite dimensional algebra and when our ground field is algebraically closed, then we can associate with our algebra a so-called quiver. So a finite oriented graph. Quiver is a collection of arrows, so it's a finite oriented graph, possibly with some relations that you have to impose. So then what does it mean? It means that I start with my algebra over an algebraically closed field, and then instead of looking at the modules, now I associate to this algebra this quiver, possibly with some relations. And instead of looking at the modules, I look at the representations. I'm going to explain what I mean by this. And I look now at the collection of all representations. So this is this category of representations subject to the relations that I might possibly have. And the nice thing is that this category is equivalent to the category of finite dimensional modules. So I can switch to representations without losing information. And representations are quite handy to work with. Let me show you an example. So we saw before as an example of an algebra the lower triangular matrices 2 by 2. The quiver, yes, that corresponds to this algebra is this quiver with 2 vertices and 1 arrow. And when I say the algebra is given by this quiver, let me be more precise. What I mean is that our algebra is isomorphic to the path algebra of this quiver. So what is the path algebra? So I take a quiver and I look at all paths in this quiver, so all concatenations of arrows. And then with this information I can define an algebra. So I take as a vector space, the vector space having as a basis all these paths. And as a multiplication, I take concatenation of paths, where this is possible, so where 2 paths can be concatenated. And if not, if they can't be concatenated because one doesn't end where the other starts, then the multiplication is 0, the product is 0. In this way I get an algebra, and which is called the path algebra. And so let's do it for this quiver. So what do we have? Which paths do we have? We have certainly the path given by this arrow. And then we have two further paths, which are called the lazy paths or the empty paths. So in each vertex, you have an empty path, which is the path where you don't move, the lazy path. And so we have these three paths. And now here I have already written down how the bijection goes, how the isomorphism goes. So to the lazy path in the vertex 1, I associate this matrix, to the other lazy path, this matrix, and to the arrow, I associate this matrix. And this is a bijection between the two bases, and one checks that it is compatible, that the two multiplications behave well, fit together well. So, okay, so that is the quiver that is associated to A. And now, what are the representations? So, when we have a quiver, what is a representation of this quiver? We associate to each vertex, we associate a vector space, and to each arrow, we associate a linear map. And so in this case, there is not much to do. So we have two vector spaces, one for each vertex and one linear map. That is, so in fact, you could say a finite dimensional representation is just a matrix. Yeah, because here you would have k to the n, k to the n, and here a matrix, an n by n matrix. So, okay, and now I was saying that in fact it's enough to look at the indecomposable representations. What are the indecomposable representations here? There are these two trivial ones, and the third is also trivial, it's just the identity. And it turns out that these are precisely the unique indecomposable representations up to isomorphism. And we know that every representation is a direct sum of those. So we can describe everything. Yeah, we can describe everything. Let me be more precise on this as well. So there is, so I said that when we have a finite dimensional algebra or an algebraically closed field, we can associate a quiver to it, and then the algebra corresponds to the path algebra of this quiver with some relations possibly. But then we can find another quiver which describes really all indecomposable representations and even the categorical information on this representation. So also the maps, the morphisms between them. And this quiver is called the Auslander-Reiten quiver. It will be infinite in general, but it's locally finite in the sense that in each vertex there are only finitely many arrows going in or going out. And yeah, if we go back to our example, then we have already seen that these are the three indecomposable representations, and then the Auslander-Reiten quiver looks like this, and these arrows stand for certain maps which are called irreducible, which play a similar role as the indecomposable modules. So they contain the essential information on all other maps. In this case, not always, but in this case it is like that. So here with this quiver, we have all the information about the category of representations of Q. Okay, let's look. So yeah, here it is again in a more schematic form. So you have Q and then gamma. The Auslander-Reiten quiver looks like that. But now let's look what happens if I add an arrow to my Q. So now instead of having just one arrow, I have two. And then the situation explodes. So here I had just three indecomposables and one component. Here I have infinitely many infinite components describing the category of indecomposable modules. And so you see that it's easy to get something which is much more complicated. And yeah, let's look a bit more in detail at what this means. So we have these countable components here on the left and on the right. They are dual to each other. And so again, here the vertices in the quiver correspond to modules or representations, and the arrows in the quiver correspond to these irreducible maps that determine all other maps. And so now here, in the composables, the vertices, they correspond to these representations. So look again at the quiver. What are the representations of this quiver? For each vertex, we need a vector space, and for each arrow, we need a linear map. And then, for example, this, you take as a vector space k to the n, and the other vector space k to the n plus 1. And here the two maps will be the canonical embeddings of k to the n in the first n components of kn plus 1 or in the last n components. In this way you get two maps, and yeah, this is a so-called pre-projective representation, and then you have the dual thing here. These are the pre-injective representations. And these are well-behaved components, countable, infinite but countable. But then there are more complicated ones here. There are infinitely many components, infinite components called tubes. You will see in a moment why we call them tubes. They are determined by these representations that sit down here at the mouth of the tube. And they, let me see if I can do this. Okay. Okay, so they look, so you have in one, you have, I think I prefer to do like this. So you have here k and k as the two vector spaces, and for one arrow you take the identity, and for the other arrow multiplication with some element of k, and in this way you get, for each element of k you get one representation. And then there is another one, the last one, where for the first arrow, instead of taking the identity, you take 0, and for the second arrow, you take the identity. And as I said, these sit here at the bottom, the mouth of the tube. And now let me show you what I mean by a tube. So what do? We take one of these representations that I showed you before, and we start taking extensions. So first we take an extension of S with itself, and we get a representation that we call S2. Then we do the same for S2, and so on. And then we get something of this kind, where you see this corresponds to the first short exact sequence, this square here corresponds to the second short exact sequence, and so on. Okay, so this is an infinite strip. But then, if you realize that S and S are the same, S2 and S2 are the same, and you identify them, then what you get is sort of a spiral, spiraling up to infinite. And that's what we call a tube. And you get one for each element of K, and this extra one that we have at the end, that is indexed by infinity. So that means that this family of tubes, one can prove that it is indexed by the projective line. So it's an infinite family of infinite components indexed by the projective line. Okay, so now let's see what happens if we add another arrow. So then, I did not draw anything. Here we are in what we call wild representation type. So here we have finite representation type, and I will define this in the next slide. Here we have only finitely many indecomposables. Here we have infinitely many indecomposables, but we can still list them and classify them. And here there is no chance to classify. And so it's called wild. So I'm explaining it in more detail here. So what is representation type? Representation type is a measure for the complexity of the category of finite dimensional indecomposable modules. And we say finite representation type if up to isomorphism there is only a finite number of indecomposables, and then everything is under control, as we saw in the first example. And then we have this celebrated result by Drost that says that there is a dichotomy. So when you have a finite dimensional algebra over a algebraically closed field, it can be either tame or wild. And tame means that it is of finite representation type, or if not, it is still well behaved. I can still list the modules, classify the modules essentially by one parameter families, as we saw before in the example. And wild, so if it's not tame, so the theorem says, if it's not tame, then every hope is lost. Because then, what happens when the module category, or the category of representations over our algebra, contains the category of modules over any other algebra. So no hope to do any classification. So things are out of control. This is a very deep, somehow surprising result. Either it's well behaved or no chance. Okay. So now just to give you an idea of what we can say, so when we have a quiver without relations, as the examples that we were seeing before, then we can say there is a classification. This is again a result by Gabriel. There is a classification of the algebras that are of tame representation type, and this is this first list, which is a list that maybe you know because these are the same graphs that occur also in Lie theory. And so this list says that my algebra has finite representation type if the underlying, I take the associated quiver and I look at the underlying graph, so forgetting about the orientation, and then the graph falls in this list. It's one of those. Okay, these are the Dynkin diagrams. And then tame means that either it's the list of the Dynkin diagrams that we had before, or it is this list of Euclidean or Euclidean diagrams. They are also called extended Dynkin because if you look at them and compare with the list before, then you see that you get those from taking the other ones and adding one vertex and one edge. So extend a little bit the Dynkin case. Okay, so this is Okay, now let's look a bit more closely at algebras of infinite representation type, and let's look again at our example that we discussed before. So if you look at this example, what do you see? You see, so we have already discussed that these are the so-called pre-projectives, and here the pre-injectives, and here in the tubes, before on the other slide I only showed you the representations at the bottom of the tube, at the mouth of the tube, but then if you start doing these extensions and construct your tubes, as I showed you before, then you will see that the representations that you get have all this form, k to the n, k to the n. And then if we look at the dimensions of the representations here, so here what do we have? 2n plus 1, here again 2n plus 1, and here we have 2n. So that means that all integers occurs as dimensions of some representation here. Yeah? And then, and not only we do see this, we also see that for the even dimensions, we have, for every even dimension, we have an infinite family of modules of that dimension. Okay, this is what was predicted by the Brouwer-Thrall conjectures that were then proved. So the first Brouwer-Thrall conjecture tells us that for every d, for every positive integer, there exists an indecomposable module of that dimension. This is, first it was just saying that there is no bound, so that for every d you find an indecomposable module that has at least dimension d, but in fact it was shown by Bongartz quite recently that there are also no gaps. So really every number is attained. And so that's Brouwer-Thrall 1, and then Brouwer-Thrall 2. We have already seen it in the example. There are infinite families of indecomposable modules in infinitely many dimensions. So there is an infinite sequence such that for every number in this sequence there is an infinite family of modules of that dimension. So in the example that we looked at, it was the sequence of even numbers. Okay, so these are features of algebras of infinite representation type. Another feature is something that, in fact, Georges termed like this, quantity and size. So these are theorems from the 70s. Independently is a theorem obtained independently by Auslander and by Mendel and Tachikawa. So it says that an algebra has finite representation type if and only if all indecomposable modules are finite dimensional. So quantity and size is the slogan, because if you have a small quantity, then you have a small size, and vice versa. Yeah. So, okay. So that means that if you have infinite representation type, you must have large modules. And now let's turn to the large modules. So, so the theorem before says you must have some large indecomposable modules, but in fact one can say a bit more. This is a result of Crowley-Boovy. One can prove that there are infinite dimensional indecomposable pure injective modules. What are the pure injective modules? A module is pure injective by definition, I mean in this situation, if it is a direct summand of a direct product of finite dimensional modules. So it's in some sense the least step that you can do when you leave the world of finite dimensional modules. Yeah. So you have what you can do. You can take you have these finite dimensional modules. You can take a direct product and look at the direct summands of this direct product, and the modules that you get are the pure injectives. So they are still close to finite dimensional modules, but many of them are large, are infinite dimensional. And they are interesting also because one can study them also with model theoretic techniques and with topological techniques. Mainly, and this is a result originating from model theory, but that is very important also for representation theory. I will come back to this towards the end of the talk. So, so we can form a topological space using the indecomposable pure injective modules. So the points of this topological space will be the isomorphism classes of indecomposable pure injectives, and the open sets are determined by maps between finite dimensional modules. So again, we are not far from the finite dimensional modules. And so we are looking here at, we take a map between finite dimensional modules, and we are looking at the indecomposable pure injectives for which this map is not surjective. So that means, I don't want to enter into many details, but that means that you can't factor in some. There is a factorization property that fails. These are the open sets, a basis of open sets. Okay, so we have this topological space, and as I said, we will come back to at the end. So now let us look at these indecomposable pure injectives in our example. Of course, I have to take something, it's not of course maybe, but I have to take something of infinite representation type in order to get indecomposable pure injectives. So let us look at this example. And here in red, what you see in red are the indecomposable pure injectives. So all finite dimensional modules, of course, because I said it's summons of products of finite dimensional. So in particular, the finite dimensional modules are there. But then there are some other modules, some large pure injectives. Namely, you can do so think again of these tubes that were these spirals going up of maps, in fact of monomorphisms. And if you go along this spiral and take the direct limit, it turns out that what you get will be an indecomposable pure injective infinite dimensional module called a Prüfer module because it is analogous to what you do in abelian groups when you define Prüfer groups. And again, in analogy to abelian groups, you can take the inverse limit and get something that is called an adic module. So again, you do the dual construction in your tube, take the inverse limit of epimorphisms that you have there. And then for each tube you have a Prüfer module and an adic module. These are indecomposable pure injectives. And then there is a last one, which is this module called the generic module. This is, if I view it as a representation, it looks like this. And it is the only, up to isomorphism, it is the only module which is indecomposable, infinite dimensional, but is finite dimensional over its endomorphism ring. Its endomorphism ring is a field, it's kx, and if you view it over its endomorphism ring, then it's finite dimensional, and it's unique up to isomorphism with this property. Okay, now let's turn to another point of view. It's a point of view that is, in fact, not new, but that has gained importance in the last few years. So you can, when you have an algebra over an algebraically closed field, you can look at the representations over this algebra, over the associated quiver, of a fixed dimension. In fact, it's not really dimension, it's something that we call a dimension vector, but essentially that's the idea. And then the representations that you collect in this way, they form some affine varieties, and in this affine varieties there is a notion of stability. And now, if we look at the stable objects, then they have a certain feature, so they are certainly indecomposable, but even better, they have so every non-zero endomorphism is invertible. So their endomorphism ring is a Stu field. So we saw before an example, the generic module has this property. And they are called Schur modules or bricks. I will use the latter terminology. Okay, so these are some special indecomposables that show up in this, say, geometric context. And now, in the last few years, there have been some papers that shift a little bit the perspective from, say, classical representation type to, let's call it, brick representation type. So that means that instead of looking at families of indecomposables, as we were doing before, you look at families of bricks. And then we say that the algebra is brick finite if there are only finitely many bricks up to isomorphism. So instead of looking at finitely many indecomposables, we look at finitely many bricks. And it turns out that this is a really new point of view, because of course here you have trivially all algebras of finite representation type are brick finite, but there are many more, even wild algebras. There are even algebras of wild representation type that have only finitely many bricks. And so this is may be an approach that can help to understand a little better this wild territory. And yeah. And now, the nice thing is that there are a lot of analogies to what I was telling you before for classic representation type. For example, there is the weak version of Brouwer-Thrall, the classic version of Brouwer-Thrall, holds also in this setup. So there are, for every positive integer, there is a brick of dimension at least this integer. So let's look at our example again to understand what this means. So here, now in red, now you see the bricks. So all modules in these countable components are bricks, and then all modules at the mouth of the tubes are bricks. The others are not. So we have less bricks than in the composables, and then we see that the Brouwer-Thrall 1, we see it 1. The brick Brouwer-Thrall 1, we see it here because we see that for every, there is a brick of for every odd number, there is a brick of that dimension, so there is no bound on the dimensions that can be obtained. But before, what did we have before? Before we had that in even dimension we had infinite families of modules for every even number. And now we have them only in dimension 2, because the others are no bricks, are not bricks. So Brouwer-Thrall 1 has its analog. For Brouwer-Thrall 2, we have to be a bit more cautious. So what we can ask, because it's true in this example, is whether there is an infinite family of bricks of the same dimension d, but we cannot expect that for that there is an infinite number of dimensions with this property. And this is still an open question. It has been proved in some special cases for some special classes of algebras, but in general it is object of current research. Okay. Then we had this quantity and size. And also this has an analog, namely, remember, quantity and size was saying that an algebra is representation finite if and only if all indecomposable modules are finite dimensional. And here we have the perfect analog for bricks. An algebra is brick finite if and only if all bricks are finite dimensional. Okay, so, but of course, now another question. So here we are at current research. So there are many open questions. A natural question here, because we had this theorem of Crowley-Bouvi that was saying that if you have representation infinite, then you have not only an infinite dimensional indecomposable module, but even a pure injective one. So a natural question is whether we can find a pure injective large brick, and this is not known as of today. Okay. Then, now let's look again at the reduction techniques that I was telling at the beginning. I was mentioning that you can decompose the category in smaller parts, then the relevant notion is the notion of a torsion pair. You can localize and look at nicer rings, and then the key notion here is the notion of a ring epimorphism, or you can decompose your module into indecomposables. Now it turns out that this approach via bricks detects some relation between these reductions. Namely, there is this theorem that says that an algebra is brick finite if and only if there is only a finite number of torsion pairs. So this reduction by torsion pairs, you can do it only in finitely many ways. And equivalently, there is only a finite number of localizations. And here I should be more precise. When I say localization, I mean that there are only finitely many ring epimorphisms. So when I say ring epimorphisms, I mean epimorphisms in the category of rings. There are only finitely many ring epimorphisms starting in A that have this nice homological property. And so, yeah, that's a property that classic localization, say from commutative algebra, has, but it's more general than that. And when I say finitely many, of course, I mean finitely many up to equivalence, up to a certain equivalence relation. Okay, so brick finite algebras have also finitely many. So finiteness of bricks means finiteness of torsion pairs and finiteness of this kind of localizations. And now let us focus a little bit on the second point. So let me be a bit more precise about the notion of a torsion pair. So I was saying it before in words, and okay, it's not much more precise than before, but so a torsion pair is a decomposition of our category into two classes. One is called a torsion class, the other a torsion-free class. And this decomposition should not lose information, so it should have the property that all modules can be reconstructed from a module from the torsion class and a module from the torsion-free class. Those of you who know abelian groups know the prototype of this, where everything starts, no? Torsion groups and torsion-free groups. This is a torsion pair. And yeah, and when I say reconstructed, I mean, what do I mean? I mean that every module has a submodule, a maximal submodule, which comes from the torsion class, such that the quotient is in the torsion-free class. Yeah? So knowing the torsion and the torsion-free class, I know everything. By doing this kind of extension, I know all the other modules. Okay, so that's a torsion pair. And yeah, let's look at some examples. These examples maybe are a bit misleading because these are even split torsion pairs. I have one, and then on the next slide I have another one. These are even split torsion pairs. It's not what I was telling before, that there is a submodule. It's even stronger. Every indecomposable module is either torsion or torsion-free. So every module is a direct sum of a torsion plus a torsion-free module. So it's even nicer than what in general is required from a torsion pair. And so here it's always our example, and I'm choosing now this as a torsion part and this as a torsion-free part. I forgot to say one thing when I showed you this Auslander-Reiten-quiver. I forgot to tell you that traditionally, we write the components in such a way that the morphisms go only from left to right. So there are no morphisms in this direction. They are all zero in this direction. And then it's not so surprising. If you know what a torsion pair is, you know that one of the requirements in the definition is that there are no maps from the torsion to the torsion-free modules. And yeah, this is true here because of how the modules work. Okay, so this is one example, and then let's look at another example. What could we do to these modules, to this component here? We could add one tube, and that is still a torsion class. Still, there are no maps from here to here, and still every module, every decomposable is either there or there. Okay, so these are these two examples. And now the nice thing is that we can order torsion pairs by inclusion, say by inclusion of the torsion classes. If the first torsion class is contained in the second one, then we say that the first torsion pair is smaller or equal than the second. In this way, we get a partially ordered set, but it turns out that this is even a complete lattice. Okay, so we have this lattice that is usually denoted tors A of all torsion pairs in the category of finite dimensional modules of our algebra. And it's a complete lattice. We can look at the Hasse diagram. And of course, by what I told you, by the way our order is defined, arrows in the Hasse diagram correspond to minimal inclusions. Yeah, so correspond to inclusions of torsion classes where I can't put anything here in the middle. Back to our example. So we had this green torsion pair where we were cutting here, and then we said we could also add a tube to the torsion part, and we have the red torsion pair. And now the picture shows us that U is contained in T, so the green torsion pair is smaller or equal than the red torsion pair. And this is even a minimal inclusion because, I mean, one would have to know better how these tubes work, but as soon as you add to U some element from the tube, you have to add everything. So there is nothing in between. I can't squeeze in here another torsion pair. So this is a minimal inclusion, so it's an arrow in the Hasse diagram of this lattice. Yeah, and now let me, in the last few minutes, let me come to my own research. So this is a problem I have been working on in the last years. So we have seen that if we have a brick finite algebra, then we have finitely many torsion pairs. And I have not told you, but there are techniques in order to describe the lattice of torsion pairs in this way. And so then one can say that we know this lattice. But what happens for brick infinite algebras? Can we say something? And yeah, then, so we have together in joint work with Ivo Herzog and Rosanna Laking and Francesco Sentieri, we have this result that says that if you have a brick infinite algebra, then, I mean, it's stated in a vague way. I hope to make it a little bit more precise in the next few slides. So then the lattice is described by this Ziegler spectrum. Remember, the Ziegler spectrum was this topological space built from the pure injectives. And, okay, and a bit more precise, it means that the torsion pairs are in bijection with something that we call with cosilting pairs, so-called cosilting pairs. And these cosilting pairs are formed taking certain closed sets in the Ziegler spectrum. And the minimal inclusions, so the arrows in the Hasse diagram, correspond to so-called mutations. So let me try to say something more. So what is a cosilting pair? I will not enter into many details because it would lead us far. In order to explain what a cosilting pair is, I would have to go to the derived category. This would be, it's not the appropriate place now to do this, but just to give you an idea. So it is a pair which is given by a closed set in the Ziegler spectrum, that it's the first component, is Z, and a set of indecomposable injective modules. So I don't know whether everybody knows what injective modules are. These are some special modules that have, that are central in representation theory. And okay, and they are some very nice pure injective modules, let's say it like this. And okay, and we want that these two sets, Z and I, have a certain property which, as I said, requires the derived category. I will not explain this, but just tell you that this means, roughly speaking, it means that these modules in Z and I correspond to a set in the derived category that has some orthogonality property. And Okay, so they are orthogonal to each other in a sense that should be more precise. And they are maximal with this property. So this is a Koselleck pair. Yeah, and now when we have a Koselleck pair, then we can produce a torsion pair out of it just by taking as torsion class, we take the modules, the finite dimensional modules that have no maps to this closed set in the Ziegler spectrum, to these pure injectives that we have chosen. And then the torsion free class is then determined by T. T determines F and vice versa. So the torsion free class will be the modules that are orthogonal on T, have no maps from T. So, and in this way, with this, we get an assignment from Koselleck pairs to torsion pairs, which turns out to be a bijection. So we have a bijection between torsion pairs and Koselleck pairs. And under this bijection, minimal inclusions of torsion pairs correspond to something that is called mutation. Mutation is an operation that occurs in many different contexts. It occurs in algebraic geometry, in the theory of cluster algebras, and in representation theory. And again, it would lead us too far to give details on this. Let me just show you the example so that you get a feeling of what it means. So let's look again at our two torsion pairs that we saw before, the green one and the red one. And we already know that U in T is a minimal inclusion. And now this torsion pair UV corresponds to a closed set in the Ziegler spectrum. The corresponding closed set is given by this generic module. This was this unique module that is infinite dimensional but finite length, or finite dimensional over its endomorphism ring, and all Prüfer modules. Remember, the Prüfer modules were the direct limits from the tubes. Okay, so that's the Koselleck set that corresponds to the Koselleck pair that corresponds to this torsion pair. And to this torsion pair, what do we get? If we do this bijection, follow the bijection, then what we get is, again, the generic module, the Prüfer modules from the tubes that remained torsion free, and from the torsion tube, the tube that has become torsion, I don't take the Prüfer, but I take the corresponding adic module. And this is an example of what we call mutation. So what we do is we take the one Prüfer module, remove it, and replace it by an adic module. That's an instance of what we call mutation. And then as an upshot, we can say that, we wanted to understand this lattice of, the original goal was to understand the category of finite dimensional modules over an algebra, and then we have seen that it is a very difficult problem, so sometimes we have to reduce, and for example, we could look at the torsion pairs instead, and we have seen that the torsion pairs, when the algebra is brick infinite, like in this case, the torsion pairs are infinitely many, but they form a lattice, and this lattice can now be approached, can be studied by looking at certain closed sets in the Ziegler spectrum and looking at mutation. And our hope is that this will help now to describe some things in terms of topological properties of the Ziegler spectrum. Yeah, we hope that this will be a tool that will help to proceed. Okay, so thank you very much for your attention.
Thank you very much, Lydia. Are there any questions or comments?
I have a question. you said earlier that there was a theorem by Gabriel with which we could characterize a ring in finitely generated algebra over an algebraic closed field, right? Looking at the associated quiver. So if it was a Dynkin diagram, then if and only if it is a Dynkin diagram, then we could conclude that the algebra is a finite type, right?
If it has no relations, I mean, it was a characterization.
Without relations.
Yeah.
So is there a similar theorem that works for works for Greek finite algebras?
That would be nice. There are, in some special cases, for some classes of algebras, there are classifications of Greek finite algebras, but in general, we don't know. And I mean, it is also a new concept, so maybe ask me in 10 years, I don't know, but yeah, at the moment we don't know. Yeah.
Daniel?
So, not all the inclusions are, all the minimal inclusions are with by one element. I mean,
No, the minimal inclusions correspond to irreducible mutation, where you just exchange one element.
Yeah, but can there be some minimal inclusions of torsion pairs where the difference has many objects?
No.
Okay.
No, these are then these wide intervals. They correspond to this more general notion of mutation, where we really exchange a bunch of objects, but it's no longer a narrow. It's a wide interval in the lattice.
Okay.
Yeah.
Thanks.
Any more questions? I have a quick one. So, when you spoke about the tame-wild dichotomy for representation type, is there any sort of result of that kind of flavor for brick infinite algebras? Is there no notion of brick tameness or brick wildness?
No, there are some notions. I think there are some attempts, but I think, it's more questions than results. There is some brick tameness, some notion, but I think from different authors, different notions of brick tameness.
So no general agreement on what should be
I think
the...
this is really still work in progress. Yes.
Thank you. Any further questions? That is not... Daniel?
So if you have a torsion pair and then you take the torsion test, can you mutate if you take any object, can you mutate always?
No, unfortunately not. And I mean, you see this. I mean, you see here that there are some torsion classes that are not covered by so that for example, if you cut here, then this torsion class, there is no torsion class in which this one is there is, if you call this U, there is no T such that U is a minimal and in T is a minimal inclusion, because you have infinitely many things here and you can still approach a little further. So that tells you that on the other side there is some co-silting pair that doesn't, where there are some points that don't admit mutation. And this is another open question, how to characterize these points. So we know, what we know so far is that if you have the points at which we are allowed to mutate, they can be described, so they have the property that they are isolated in the Ziegler spectrum. So we can, it's topological condition, but at date we can't say that the converse is true. It's true in some cases, in say for hereditary algebras, for domestic string algebras and so on. It's true, and these are precisely the isolated ones. But it's something, Rosie spent the whole summer, I think, trying to prove this. We don't know the converse in general. And yeah, any suggestion is welcome. Yeah.
Further questions? Danielle? Any further questions? Well, if not, let's thank Lydia
Yeah, thank you
again.
very much.
Thank you.